Now let's talk about what image noise is. Now, first of all, before trying to understand what image noise is, why we see noise in image. So there are a lot of reasons for that. We can have like light variations. We can have noise due to camera electronics, how it was captured. There might be like some fault in the hardware which is actually used for taking that photograph, right? The sensors or the lens. It could be there due to like surface reflectance. It's not always uniform. It could be due to lens. There might be some dirt on your lens, right? Or the lens, the hardware itself might not be perfect. So a lot of other reasons why you have noise in your image, and noise is random. And one important property is it occurs with some probability, all right? It won't occur like all the time. So there will be some probability associated with whatever noise you see in your images. And because it has some like probability, so it will have some kind of distribution. So if it has a distribution, what we can do is we can represent, like we can model this noise. And a very simple way to do that is, for example, if you have an original image which is completely noise free, right? We call this I original. And this is a function xy, you know that this is like these are the grid values. So this function will give you the true pixel value without having any noise. Okay, for example, this is the image. And then let's say at each pixel xy in that grid, we have some kind of noise, and we can represent that using this function small n. Right? So if we have to introduce this noise into this original image, the image model will look something like this. So this will be the actually observed image. What we will see, we'll have this original function, which represents like images without any noise. And we just add like the noise function. Okay, so this is one way we call this additive noise, because we are just adding noise to each of these pixels. We can have a different model where we can say that instead of adding, we can actually multiply noise. So that's called multiplicative noise. We can have varying kind of models. So let's not worry about like how it's represented, but let's try to understand like, okay, we can have this kind of model. All right. So this is the clean image. And let's say we had some noise, which was given by this function. And what will happen is you will see image like this. So this is like the observed image when you have noise in your sample. All right. So this is like the example of multiplicative noise, which I was explaining earlier. Instead of addition, what you do is you take that noise and you multiply that with the pixel value. And let's say if you have multiplicative noise, some function, then you will observe image something like this. Okay, so the most common form of noise can be represented using Gaussian function. We call this a Gaussian noise. And Gaussian function, you almost remember like from your maybe probability course, it's a curve like this, right? And this is like a very simple equation of Gaussian. From left to right, you will get these values. So this is kind of range of this function. And you can see that the maximum value of Gaussian is around 0, which is mean of this Gaussian function. All right, it peaks at here. And if you have like a Gaussian noise in an image, it might look something like this. But again, this will vary depending upon like what kind of Gaussian function you use. Okay, and the most important variable there will be this standard deviation. What's the standard deviation of the Gaussian function you are using? That will define what kind of image you are going to observe. So that was one kind of noise. Other ways to represent noise is like, let's say your noise is coming from a uniform distribution. Okay, so again, this is a simple function which says if your value is less than, let's say, a over here, if it's towards the left, your response will be 0. Right? The function will return 0 all the way up to negative infinity. And if the value of the domain is greater than b, all the way up to like plus infinity, again the function will return 0. But between a and b, your function is going to give this value. So it's kind of a positive response. And the positive response is only between a and b. And it's uniform because this value is not changing. Gaussian, you can see that from negative infinity, it was close to 0, but it was gradually increasing, right? Then it was peaking at the mean, which was 0, and then gradually going down. In this case, it's different. It was completely 0. So this is kind of a step function. Suddenly it's 1 or whatever this value is. So this is like 1 over b minus a to just normalize it. And then again, it goes to 0 and it will remain 0. Okay, so this is a very simple step function. And this is like also uniform distribution. And if we take like a noise from such a distribution, we call that salt and pepper noise. And the idea is like you will make each pixel in your image either black or white with some uniform probability. All right. So each pixel you will decide whether you will add noise or not, and then you will decide whether the noise should be like 0 or 1. So that will come from the step function. Either you will make it completely 0 or you will make it completely 1. So let's say if this is the original image, and if you have salt and pepper noise, it will look something like this. And you can see here that some of the pixels are like completely 0 and some are completely 1, assuming that the range of this image is between 0 and 1. Right? And other pixels, you won't change at all.